So now the last problem we talked about used torque to learn about something. This time I want to try and do an energy problem. And this is buffered. So now, whoops. All right, so let's take a look at page 73. So this is the second to last piece of chapter 10 that we need to cover, swinging motion. And the idea here is we've got some pendulum here. Okay, and there's going to be a pivot point. Trying to draw the picture that you've got there. There might be some angle. And maybe we'll even throw a point mass on it. Okay. Now, in this case, what's critical when we're doing energy motion, swinging motion, and I'm going to say rotational kinetic energy method. Okay, and so what's critical is when something like this is moving, we need to know where the center of mass is. So let's say for some reason the center of mass ends up being right here, COM. Related to that, we're going to want to talk about the radius for the center of mass. I'll call this RCM. And I don't know if I use capital R or lowercase r, but I think I used lowercase r in the book. Let's try and use that. All right. Now, to be clear, you're going to have to do a quick center of mass problem to figure this out in any real life application. So typically, we would know the center mass of a uniform rod is right at its center. We know the center mass of the point mass is right here, and you'd have to do a quick x1, x2, m2, 1, 2, or x1, m1 plus x2, m2 over m1, m2, that kind of this. Sorry, let's just write it. You know what I mean by that? You could use that formula to figure it out. And what you do is basically align the x-axis here, and then you'd have to pick a coordinate system. And typically when we do that, we say this, the pivot is x equals 0. The pivot becomes kind of like your origin. All right? So you could figure out the radius of the center mass. By doing that, this is equal to the radius of the center mass. I'm confident you can do that. Why is that important? The energy method, right, when we're usually doing this, we talk about kinetic energy initial plus potential energy initial plus work external and non-conservative is equal to kinetic energy final plus U final, potential energy. The gravitational potential energy is based on this reference level. And when it swings down here, that's going to swing in a slightly smaller circle than the point mass. So this is the height of the center of mass, right? So we would typically call this height equals 0, and this one would be height initial. Does anybody remember the quick shortcut for figuring out height initial for an object curving in this circular motion? If we use the angle to the vertical, this is the quick shortcut. So by doing this, notice what we have to do. We use some geometry to get the initial height. And then from that point, we use the radius of the center mass. So you can get the initial height for gravitational potential energy. Does that make sense? Well, let's remind ourselves for translational kinetic energy, what was the formula for kinetic energy? K equals 1/2 mv squared. That was our old formula. For rotation, what is going to be our formula? K is equal to 1/2. What's the rotational equivalent of mass? I, moment of inertia. Yes. What's the rotational equivalent of V? Somebody other than Jacob.
Omega.
Omega. Good job, though. I appreciate it. Well, I hope you can see this. We're going to have 1/2 I omega initial squared plus mg height initial plus, what do you think the work done by air resistance is if we're trying to solve this problem today? Yeah, we're going to ignore drag and friction. What about the work done by the pivot, the force at the pivot? Right? The pivot has to exert a force to hold this thing up. Is the pivot moving? What's the displacement of the pivot? What's the displacement of the pivot if it's not moving? Zero. So what's the work done by the forces at the pivot?
Zero.
Yeah. So the work done external, what about, do you agree this rod's going to be under tension? Right? You're hanging a mass on it. The mass is going to pull down on it. There's going to be tension in the rod. The tension is going to be pointing this way. Is that going to do any work? Why not? Yeah. So for these reasons, if we ignore drag and friction, tension's perpendicular, forces at the pivot, doesn't matter, there's zero displacement, what's going to happen to this work term? It's going to drop out. So that's why we could drop this out. Now, wait a second. What is this mass? Is it the rod's mass or is it the point mass? What's that? It's both. So here I've got to do rod plus the point mass. Which object is swinging? Is it the rod or the point mass or both? So what do you think we need for the moment of inertia? Is it the moment of inertia of the rod, the point mass, or both? So for both of these terms, you got to do a little bit of work. In particular, you've got to do a little bit of math. You've got to do I total equals I1 plus I2, just like mass equals mass 1 plus mass 2. What do you think of that? That's the basic idea. So you're going to do this problem in the lab in a minute, but maybe we do one of them together before you do that. That way you can see as we plug in numbers here. Is that all right? Or I don't know. That's what I was thinking. We do one together. Does that sound good?
Yes.
All right. So I'm going to leave this up here for reference, and I'm going to go over to the other board and do one. Okay. Let's just start with 10.48. Let's remove the point mass and make sure we can get this thing right without the point mass, and then you can add in the point mass for the lab. 10.48. We've got a pendulum. I think it's initially at some angle theta. Pivot has negligible axial friction, so we don't have to worry about the work done by friction at the axle here. Okay. Held initially at theta, released from rest And what do we want to get? Speed of the end of the rod at the lowest point in the swing. So this is what part A says. Speed of end of rod at lowest point in swing. That's our goal. I need some information from you. When I say the word speed, what variable do I usually mean for speed? Meters per second. That's the units of it, which is what variable? V. Now, the trick is a lot like the last problem. Remember in the last problem, if you wanted to get acceleration, we would first solve for angular acceleration, then multiply by radius. So what do you think the trick is going to be here? First, solve for omega, multiply by correct radius. That's the way we usually do it with these problems. That's kind of a practical thing. Why is that? Every point on the rod has the same RPMs. Every point on the rod has a different speed. They have the same rotation rate, the same omega, but each point on the rod will have a different speed in meters per second. Okay. Well, I'm going to write down my energy equation. Remember, when you see something asking about speed, that's a good sign that we might want to do an energy problem instead of a torque problem, right? Right? Remember when we did it previously? If we talked about acceleration, we would usually do forces, and if we talked about speed, we would do energy. Now the same thing is true. If we're talking about angular acceleration, we do torque. If we're talking about speed, we'll do energy. Doesn't always work, but usually. Okay. We've discussed this just a minute ago. For reasons we just discussed, we're going to say the work is zero. What's the initial kinetic energy? Why do you know it's zero? I believe you. What's the key words in the problem that help you know it's zero?
Release from rest.
Release from rest tells us K initial equals zero. Okay, good. Do we have any springs in this problem? No, so I don't have to do spring energy, right? What's the only type of potential energy we're going to have? Gravitational. Whenever we did energy problems, what was one of the first things we did if we had gravitational energy? Set a reference level. Where do we set the reference level?
The bottom of the swing so that we can take out the.
At the bottom of the swing. But which part of the rod's bottom of the swing?
The end of the rod.
No. And now, so here's why. What we want to do is we want to deal with omega, right? And then multiply. You're right that at the end, we're going to multiply by the entire length of the rod. The trick is when something is swinging, what did I just say on the other board? That everything has to be referenced to for gravitational energy? The
Center of mass.
center of mass. So the trick is we got to know, well, for this one, it's a uniform rod. Where's the center of mass? L over 2, right? There's the center of mass. We need the lowest point of the center of mass. Is that cool? So I'm going to draw that as a little circle here. And I'm going to draw this over. This would be height initial. This would be height final equals 0. So I'm going to set the lowest point in the problem, the bottom of the swing is height 0, for the center of mass. And that's what's a little different now. Is that good? Yeah. Okay. What's height initial going to be? We know the radius to the center of mass is L over 2. Agreed? Did I say the length of the rod was L? Yeah, okay. So let me write this here. Rod has mass M and length L, just because that was written in the problem statement. Sorry, I'm just getting organized. That's why I knew this was distance L over 2. What's height initial for this weird kind of setup?
L over 2.
L over 2 times 1 minus cosine, right? If it was all the way up parallel to the ground, then it would be L over 2. If it's at some angle to the vertical, it would be this. If your angle was to the horizontal, how would this equation be modified? What happens to all your sines and cosines when you switch angles from horizontal and vertical? They flip. So if I had drawn the angle to the horizontal, you could do a 1 minus sine, right? Because this would become 90 minus theta. Maybe I'll just mention it like this. Sine of, how about I say it like this? Cosine of 90 degrees minus theta happens to equal sine of theta and vice versa. So this is a cool trick you could use to get rid of 90 minus thetas in any of your work. So if I ever draw it in a weird spot, you can use that relationship. That said, we don't need that here because the angle is drawn to the vertical and we know that result. I'd like to pause and make sure you're good on the heights. Now in this case, we don't have to worry about two masses. I can get the initial energy. The gravitational energy would be mg height initial, and I know an equation for it. What's the final gravitational energy? 0. Because we set height final equals 0. What equation should I use for the kinetic energy? 1/2
B squared.
No.
I omega squared.
I omega. So if we had one object that was translating, we would use the 1/2 mv squared. In this case, we have a swinging or a rotating object. We got to use the new moment of inertia term, which is I omega squared. Well, before we plug in all the garbage, let's solve for the thing that we will help, right? If we can first solve for omega, then multiply by the correct radius, we've got the speed we want. And that's the new style. Got it? So rather than plug everything in first solve for omega, then plug in a bunch of crap. You know what I'm saying? Okay, what's omega then? You can do this in your head, right? All right, maybe not. You guys want to work through it? What is it?
2 divided by I.
Now, I'm looking for speed. Do I need to worry about plus or minus? Positive, so we don't care. Got it. Now, help me out. It's 2 mg. What's the height initial? Yeah, that's that stupid thing we figured out. Got it. What's the moment of inertia for this particular object with that particular choice of pivot and that particular orientation of pivot? Do you remember? If not, what page was it on? Like 53 or something? What is it?
1/3
I think you're right. A rod at the end is 1/3. Rod at the center is 1/12. You're going to use those two so much, you're going to have them memorized. Whoa. What cancels out? Mass. Okay, that means, shouldn't this, I guess you could make the rod out of lead or wood, and it should be the same rotation rate at the bottom, as long as all these frictional and air resistance forces are negligible. Can we clean this up? Oh, I guess the 2 also, doesn't it? Let's rewrite this. It's getting too messy. I can't follow. I could have popped the 3 upstairs, and I think one of the L's. Is that what you said somewhere? Yeah, nice. I didn't even see that at first. Good. But the 3 will pop up. And so we're going to get 3G over L, because there's a G and an L left. The 3 came up. 1 minus cos. Is that right? Double check that. It's a big mess. How could we check this result? What are the units inside? Well, we got a square root of meters per second squared times 1 over meters. What are the units of this garbage? No units. I get 1 over seconds. That's still on the screen? Just barely, okay? Wait a minute, what are the units of omega over here? Is that the same? Nice. Okay. And so at this point, you can actually plug in some numbers, plug in an angle, tell the computer the length of the rod, run the simulation that you just did, and get the value of omega at the bottom and see if it matches. Agreed? But now what we want to do is, it turns out very oftentimes we're going to have problems where you have an impact with a lump of clay, and so there will be a point mass sitting somewhere on this rod. And so the main difference is, I want to go back to our first screen. If there's a point mass in here, what is the extra level of difficulty? Well, you got to get the combined moment of inertia and the combined mass. And we also need to get the center of mass radius using the center of mass formula. Same crap piece of cake, right? I have a fun one for you. Couple of fun ones. All right. Let me see if I can do this here. Now let's do this right here. Just so we got this on Zoom. I got these 2 pendulums. Take a look at problem 10.49 really quick while I get the camera set up. Read 10.49 for fun. I'll just go up here. And you can discuss that with your neighbor while I'm getting this set up. Okay. So hopefully you can see there's a couple of pendula here. And the question that I was going to ask you is, and maybe let me zoom out just a little bit more. What I want to do maybe is erase some of this junk on the board here. I'll just move our result here over here just in case I need it. I'm going to erase this on the board so you can see it better. My question is, which one of these should be moving faster when it gets to the bottom? You've got a short one and a long one, right? What do you think? Any guesses, class? Why is that? Oh, I heard a short and a long. So why do you think short? Why do you think long?
The short one center of mass. Take less time to reach the bottom of the arc because the other one center of mass will be farther down.
So the other one's center mass has to travel farther. True. Which one is going to have more torque exerted on it? Or what were you going to say?
Well, what I was going to say is that yes, the short one should reach the bottom first, but the long one should have a better, speed. Or
So, okay,
Yeah.
true. We expect points farther away, right? Look at the distance, right? This one's gonna have a much larger R times omega. It's quite possible this could be a larger speed.
Right.
But the one that gets down first should have a larger rotational speed. Do you agree with that statement? This one's gonna have more RPMs. Here's how I can tell, rather than guessing, I look at this equation. Which one should have a bigger omega at the bottom and why?
The shorter one.
The shorter one. L is a smaller denominator. That's an easier way to see it, right? So let's just do it. And hopefully for you, I'll get hit in the face and we can call off the rest of lab. It totally gets down faster, but you can even see it. It's rotating much faster, right? Now, to be fair, this point down at the end would probably hurt more if it hit me in the face. So it probably is moving with greater speed at the very end. But this one has more RPMs. So this one has more omega. Points down at the end might have more V. I don't know. I'd have to do all the math and multiply. Well, if I wanted to evaluate the length, I'd have to multiply, or sorry, the speed. Oh, we never did this, right? V, okay, let's go back to the calculation here. Remember, V is R omega. So for a point at the end of the rod, what is the radius? If I'm all the way here at the end of the rod, radius equals L, so what is V? It's L times the square root of 3G over L times 1 minus cosine theta. And notice the L can come inside and square it. The L will flip to the top inside the radical. And so exactly like you thought, we see that speeds of the end of the rod scale as the square root of L. So it definitely is true that this point is moving faster in terms of meters per second, but slower in terms of RPMs. You good?
Yeah.
And so that's kind of, and this is actually, I think, what we were supposed to find. We found the rotation rate, but that wasn't the answer to part A. We wanted the speed, which was meters per second, which was V. So this was the correct answer for part A. Okay, moral of the story. We've got to talk about rotational quantities and translational quantities. Alphas, omegas, and thetas versus V's, A's, and X's or radiuses and things like that. Got to read the problems carefully. And usually in this chapter, it's better to first solve for a rotational quantity and then multiply by the appropriate radius to get the correct translational quantity. That happened in the first problem and the second problem. You good with that? You ready to do the lab? Let's do it. So do experiment 2. I'm going to go ahead and end the live stream.